completely switching gears here, it's kind of only natural to follow up a lesson on nuclear fusion with the opposite process, which is nuclear fission, probably something that you've heard of before. And the definition is the opposite. Instead, we're splitting one nucleus and now making it smaller particles. So typically the main difference is in fusion we start with small elements and we make a bigger one. And now we're going to have a large element and it's going to split into smaller pieces. Uranium is the most common atom that you're going to see used as an example of nuclear fission because it's the element that we use in all of our, power facilities and submarines and all this stuff that operates on nuclear fission. So one of the main differences is this is not necessarily generated by heat and pressure. What happens is an atom that is already a little unstable is bombarded with another particle that totally breaks it apart. So if we take this neutron and we kind of shoot it into the nucleus of this uranium, okay, we create a very unstable situation, and then that uranium bursts into smaller pieces. So you end up with a breakdown where this uranium turns into a barium and a krypton, and then a bunch of neutrons just kind of go out on their own. The other release is of an enormous amount of energy, which is why we can use it for fuel and we can use it for weapons. Fission reactions are particularly dangerous because of these extra neutrons. So they cause what we call a chain reaction. So all of these nuclear fission things start with one neutron bombarding one atom. But since one of the products is these very energized neutrons, they're going to now shoot out and they're going to collide with other uranium atoms, and then those uranium atoms are going to explode, and then that's going to create more neutrons, and then they're going to bombard other uraniums, and it just keeps going and going and going until all of the uranium has been used up. And there's more than one way that this process occurs. They start generally the same way, so you'll see a neutron added to a large nucleus, but what they turn into varies. Okay, it's obviously not a very stable process. It's pretty wild. So there's all kinds of different products that a uranium atom can make. But the one thing that you will see in common is when you look at the masses, for example. So we have a mass of 235 and 1, so we have a total of 236. On the other side of what, the arrow works like an equal sign, 140 plus 93 plus 3 ones is also 236. So we're obeying the law of conservation of mass. Even though the large atom is turning into small pieces, all of the pieces still add up to weigh the same as when they were one atom united. Okay, there were 92 protons, and 56 plus 36 is still 92. Okay, same thing with the second one. Even though this is a slightly different result, okay, these are different daughter nuclei, we still have 236, and 144 plus 90 plus 2 is still 136. Okay, 92, 54 plus 38, still 92. The way that we can harness fission for power is if we can let a fission reaction generate an intense amount of heat. Okay, we boil water, the steam rises, and the steam turns a turbine, which is what generates the electricity. This is actually the same way that coal generates electricity. Okay, you would just use coal here. Coal would heat up water and turn it into steam. The difference is the energy from nuclear reactions is so much more efficient. Okay, you can have a way, way, way smaller mass of uranium generate the same amount of electricity as an enormous amount of coal. So to summarize this whole process, I just want to show you what you might be expected to do, which is solve for a missing portion of a nuclear equation and then identify what's happening. So we talked about the fact that this is sort of like an equal sign, and what we're saying here is a lithium is adding itself to a helium. Okay, well, if lithium has a mass of 6 and this helium has a mass of 4 and there's only one product, then that means this unknown substance must have a mass of 10. If there's 3 protons in this lithium and 2 protons in that helium, then this substance must have 5 protons. Okay, if we want to identify, we know the atomic number is the number of protons, and on the periodic table, boron is number 5. Okay, so that's how you solve for the nuclear equation. If you identify what's happening, what we're looking at here is 2 small nuclei becoming 1. So that means this is an example of nuclear fusion. And in our last example is a slightly more complicated one. Okay, we have a neutron and a plutonium, which have a total mass of 240. Okay, and on the other side, what they are becoming is a xenon, a couple neutrons, and something unknown. Well, we know that the total mass has to stay the same. And we know this weighs 134, and we have 3 neutrons, which would weigh a total of 3. So 240 minus 134 minus 3 is going to be 103. We know that this had no protons, this had 94. So we're going to have 94 minus the 54 from xenon.